The last time we met, we introduced the finite state machine. In this video, I'd like to present one worked example for the classic sequence detector. We'll build a sequence detector to detect the 10111 sequence. For example, this machine will monitor a stream of digits looking for this particular sequence. It sees it here. It sees it again here. And what will happen is it'll have a low output, and then it will go high for one cycle every time it detects this 1011 sequence. To get us started, let's review the very concept of the finite state machine. We'll start with a cloud of combinational logic known as the output logic. Next, we have a cloud of combinational logic called the state next logic. And then at the bottom are the state registers. Think of the state registers as a group of data flip-flops that advance on clock. If it helps, you could put the D here and the Q here. The input to the state register comes from the state next logic. By the way, you'll notice that this is a general flow in this direction through our combinational logic, but there's a flow this way through our state registers. If it helps, think of them as a form of feedback. The output of the state registers goes to both the output logic and the state next logic. In this drawing, this is typically a bus. Let's assume it has a width of 3 bits. This line is called the state next line, and this line is called the state line. You could say that the state of the finite state machine is held by the state registers. The state is the actual information held in Q. The output logic, of course, holds the outputs. To complete this sketch, we need to add the inputs to the system. The inputs will certainly go to the state next logic. The inputs may or may not go to the output logic. It depends on what type of machine we're talking about. If it's a Mealy machine, then the output is dependent on the input and the state. So here's the state line, here's the input line. If it's a Moore machine, then this line is absent, and the output is completely dependent on the state. Let's go ahead and write that down before we forget. So in the Moore machine, the output is determined by the state. Period. Only the state determines what the outputs will be. For the Mealy machine, the outputs are determined by the state and the value of the inputs. For today's example, we'll stick with the Moore machine, which means we're going to build a machine that looks just like this, where the output is dependent only on the state of the machine. As I said, we're going to build a sequence detector today. This is a machine that accepts a bit stream and looks for the sequence 10111. Think of it this way. We have a signal generator that outputs ones and zeros. It is sent to our sequence detector. The sequence detector is looking for a 10111 sequence. When it does detect that sequence, the output will go high for 1 bit period. Let's get started by defining a few states. Let this be state 0 and state 1. If in state 0 and the first digit encountered by our sequence detector is a 0, the machine stays in state 0. If the first digit encountered is a 1, the machine transitions to state 1. Now we add another state. Call this state 2. If we're in state 1 and the machine encounters a 0, which is to say we have a 1, 0 sequence, then we'll transition into state 2. However, if you're in state 1 and you encounter a 1, we'll transition back into state 0. For example, if we encountered 0, 1, 1, we'd end up back here. So that would be 0, 1, 1. That is definitely not the sequence we're looking for. However, if we encountered 0, 1, 0, then we're well on our way to detecting this particular sequence. Let this be state 3. If in state 2 and the digit is a 0, go back to state 0. If in state 2 and you encounter a 1, transition to state 3. 1, 0, 1 gets us that far. State 4. If in state 3 and you encounter a 0, go to state 2. If in state 3 and encounter a 1, go to state 4. That's 1, 0, 1, 1. 1, 0, 1, 1. So we're almost done. But we should talk about this path here to see if that makes any sense. 1, 0, 1, 0. So that's sequence 1, 0, 1, 0. Which means that when we're in state 3, we're effectively restarting with this 1 and 0, as opposed to going back to the beginning and throwing out the fact that we had a 1 and a 0. State 5. If we're in state 4 and encounter a 0, go to state 2. If in state 4 and we encounter a 1, go to state 5. That's 1, 0, 1, 1, 1. 1, 0, 1, 1, 1. So we've had success. We have indeed detected the sequence of interest, which means our output will go to 1, whereas it was 0 for all other states. If in state 5 and you encounter a 0, go to state 2. If you're in state 5 and encounter a 1, go to state 1. What we're effectively doing is preparing for the possibility of a sequence such as this. Here is our original sequence, 10111, but this is also 10111. It looks something like this: 1, 0, 1, 1, 1, success. We've detected our sequence, right? 1, 0, 1, 1, 1. But now watch this. 1, which is an S5, 0, 1, 1, 1. We've also detected it again. At this point, I would ask you to take this state diagram and transfer it to a piece of scratch paper, or if you're able, go ahead and print, because you'll need this information in order to construct the state table, which looks something like this. We'll start with state 0 when the input is 0, and state 0 when the input is 1. We'll encode state 0 as 0, 0, 0. Next is state 1, encoded as 0, 0, 1, with the input of 0 and the input of 1. State 2, state 3, state 4, and 5. To complete our binary count, we'll include a space for state 6 and a space for state 7, with the understanding that if we ever reach that point, and we never should, but if we did, we would immediately go back to state 0. All right, I hope you copied this state diagram because you're going to need it in order to understand what we do next. If we are in state 0 and the input is a 0, we stay in state 0. If we're in state 0 and the input is 1, we move to state 1. If in state 0 and input 0, stay in 0. If in state 0 and input 1, move to 1. If you're in state 1 and the input is a 0, move to state 2. Otherwise, move to state 0. If in state 1 and the input is a 0, go to state 2. Otherwise, go back to state 0. Let's take a look at state 2. So if we're in state 2 and the input is a 0, go back to state 0. If in state 2 and input is a 1, go to state 3. So state 2, input 0, go to 0. Otherwise, go to 3. Let's look at one more, and that is from state 3. If in state 3 and you encounter a 0, go to state 2. If in state 3 and you encounter a 1, go to state 4. If in state 3 and the input is a 0, go to state 2. Otherwise, go to state 4. Here's what we do for state 4 and state 5. As far as the output is concerned, it should be 0 for all conditions except state 5. Now that our state table is complete, let's add a reminder that this here is S2, S1, and S0. This is input. We'll just call it I. Here we have the N2 bit, the N1 bit, and the N0 bit. Our next move is to determine the logic for our state next. That's going to require 3 K-maps. A K-map for N2, a K-map for N1, and a K-map for N0. Normally, we'd also do a K-map for the output, although for this particular case, if we detect the bit sequence 101, we're good to go, and we can set the output based on that. Once again, I would ask you to transfer this to scratch paper or to print it out because you're going to need it in order to visualize what we're doing with the K-maps. Our inputs to this K-map are S2, S1, S0, and I. And we'll let this particular K-map be for the N0 bit. We'll let this be the N1 bit, again with S2, S1, S0, and I. And finally, we'll construct a K-map for the N2 bit with inputs S2, S1, S0, and I. If we're in state 0 and the input is 0, the states will be S2 naught, S1 naught, S0 naught, I naught. The N0 bit will be 0. That's transferred in the table like so. If we're in state 0 and the input is 1, that would be S2 naught, S1 naught, S0 naught, I. The N0 bit will be 1. If we're in state 1, the N0 bit will always be 0. If we're in state 2 with input 0, that would be S2 naught, S1, S0 naught, I naught. The N0 bit will be 0. If state 2, input 1, N1 is 1. At this point, you can see we're just walking down this column, adding the values to the K-map. So that's 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, and all else is 0. That brings us to the N1 bit, and once again we can just walk down this column. So 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0. Everything else is 0. And finally we arrive at the N2 bit, where we once again just walk down the column. 0, 0, 0, 0, and 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, correction, 0, 1, 0, 0, and everything else is 0. All right, give me a moment to double check everything. It looks like there's a mistake right here. That should have been a 1 and a 0. Does that look better? So 0, 1, 0, 1, 0, 1, 0, 1. Yep, all better. We can now go ahead and record the Boolean equations. N0, combine those, we combine these, and we combine like so. That's S2 naught, which is the first two rows, and then S0 naught I, or S1 naught, S0 naught I, or, now we'll get these two. So that's S2, S1 naught, and I. As for the N1 coverage, these two combine, these combine, and that one is by itself. So that's S2 naught, S0 I, or S2, S1 naught, I naught, or the one by itself, S2 naught, S1, S0 naught, I, and finally coverage on N2. Looks like we'll need 2 4-input AND gates for that. S2 naught, S1, S0, I, or S2, S1 naught, S0, and I. Once again, let me double check my notes, make sure I haven't made an error. All right, that's good enough. Let's go over to CircuitVerse and see if we can't build this circuit and then test it to see if it performs as we expect. Start with 3 data flip-flops for the state registers. Using the array style, let this be S2 and this be S2 not, S1, S1 not, S0, and S0 not. Here's the input, which is represented by this line here, and input not. We'll use a button as our clock signal. We'll start right here with the N0 input. From our K-maps, we know that that takes 3 input AND gates. Remember, you can increase the size using this AND gate properties block. Those AND gates are connected to S2 not, S0 not, I, and let's see, this one is S1 not, S0 not, I, and S2, S1 not, and I. A 3 input OR gate. We'll join these all together. That takes care of N0. Now, let's work on N1. If you hold the Shift key and then drag like so, you can move all of these at once. From our K-map, we know that N1 requires 2 3-input AND gates and 1 4-input AND gate, with a 3-input OR gate to tie them together. S2 not, S0, I not, S2, S0 not, and I. And for the 4 input, it's S2 not, S1, S0 not, and I. And now the last one is N2. From our K-maps, we know that takes 2 4-input AND gates. S2 not, S1, S0, I, S2, S1 not, S0 not, and I. Our last step is to construct the output logic. We said that was relatively simple for this particular case, because all we're going to do is look for the state 5. So that's 1, 0, and 1. You can even add a digital LED to see when we've met that state. Now we reach the moment of truth. Chances are it's not going to work, but we'll try it anyway. Let input equal 0. If we push the button, we should stay in state 0. So 0, 0, 0. So far, so good. If the input is a 1, we should move to state 1. If the input is a 0, we should move to state 2. This is looking good so far. From state 2, If the input is a 1, we should move to state 3, which has happened. Excellent. Now we should move to state 4. And something's gone wrong. That light should not be on because we're not in state 5 yet. And I can see the error right there. So let's break this line. If we're in state 4 and the input is a 1, we should move to state 5. And we didn't, so something went wrong. S2 naught, S1, S0, I, S2, S1 naught, S0 naught, I, and that looks good. S2 naught, S0, I naught, S2, S0 naught, I. This should be an I naught. There we go. Let's give that a try. So go back to state 0. So 1 brings us to state 1. A 0 should bring us to state 2. With a 1, we should go to state 3, state 4, which we are, 1, 0, 0, and now to state 5. Success. So we've made our way around that loop. And you see the light did come on when we're in state 5. All we need to do now is test all of the other loops to make sure we're successful. So let's go back to state 0. I hope you have that state diagram in front of you so you can follow along. Anywho, if in state 0 and 0, stay in state 0. If in state 0 an input is a 1, go to state 1. If in state 1 an input is 1, go to state 0. If state 0 and 1 go to 1, if 1 and 0 go to 2, very good. If in state 2 and 0 go back to 0, excellent. So I'm going to advance to state 2. All right, so now we're in state 2. If 1, go to state 3. If 0, go to state 2. Excellent. Let's go back to state 3. If 1, go to state 4. If in state 4 and 0, go back to 2. Very good. Let's advance back to state 4 now. If 1, go to state 5. From state 5, if it's a 1, we should go back to state 1. Excellent. Let me advance back to state 5 now. If in state 5 and 0, go to state 2. Uh-oh. Glad we checked that because there's one more error in here somewhere. So give me a moment, see if I can find it. Looking back over the notes, I think I found it. It's here. This should have been S1 naught. And it turns out there was a redundant term which I'm going to remove. Let's test it first, and then we'll go back to the K-maps to see where I led you astray. 1, 0, 1, 1, 1. The light should come on. Now, if we're in state 5 and the input is 0, we should transition to state 2. Yes, there it is. Okay, good. Looking back at my notes, it turns out I had just transposed a number incorrectly. I had mistakenly written this as S0 naught. So it turns out the K-maps are good in that regard. It was just my mistake. As for that AND gate I removed in the N0, this provides coverage for those two min terms. And this provides coverage for those two minterms. That's all that's needed. It is not necessary to add this term. As we finish up, I'd like to point out that this circuit is composed of three major sections. At the top is the output logic, which in this case is arguably very simple. In the middle, this array style, this cloud of combinational logic, determines state next, which is represented on these three lines here. State next goes to the D input of our three registers. And of course, the registers hold the state of the machine. That's represented as S2, S2 naught, S1, S1 naught, S0, S0 naught. And finally, this line is input and input naught.